What are quantum error correcting codes for quantum tech? Have you ever wondered how quantum computers manage to keep their delicate information intact? Today, we will discuss the fascinating world of quantum error correcting codes and their role in quantum technology. Quantum error correcting codes are specialized methods designed to protect quantum information from errors that arise due to noise, decoherence, and imperfections in quantum hardware. Since quantum states are quite fragile, these codes are essential for maintaining the integrity of quantum data and ensuring reliable quantum computation. In quantum computing, information is stored in quantum bits or qubits. Unlike classical bits, which can only be in a state of 0 or 1, qubits can exist in superpositions of both states. This unique property makes error correction more challenging. Errors can affect the value of the qubit, known as bit flip errors, and the relative phase between states, referred to as phase flip errors. Quantum error correcting codes must be capable of detecting and correcting both types of errors to preserve the quantum state. The core concept of a quantum error correcting code is to encode a single logical qubit into multiple physical qubits. By spreading the quantum information across an entangled multi-qubit state, if some physical qubits experience errors, the original logical qubit can still be recovered through a decoding process. For instance, the simplest 3-qubit code encodes one logical qubit into 3 physical qubits. This allows for the detection and correction of single-qubit errors. Several well-known types of quantum error correcting codes exist. The repetition code encodes a qubit by repeating it multiple times, which can correct bit flip errors but not phase flip errors. The shear code encodes one logical qubit into 9 physical qubits and can correct either one bit flip or one phase flip error. The Steen code is a 7-qubit code that can correct both types of errors and is fault-tolerant, meaning the correction process itself does not introduce additional errors. The surface code uses a 2-dimensional lattice of qubits and has a high error threshold, making it promising for scalable quantum computing. The Hastings-Haw code optimizes spacetime costs in certain quantum architectures but may have high overhead in gate-based systems. Quantum error correction involves measuring certain properties of the encoded state, known as syndromes, to detect errors without collapsing the quantum information. These syndrome measurements allow the system to identify and correct errors in real time, enabling the quantum circuit to run successfully without needing multiple attempts. In practice, quantum error correcting codes are fundamental for advancing quantum technology. They allow quantum computers to operate reliably despite the noisy nature of current quantum hardware. This reliability enables longer quantum computations, more complex algorithms, and the scaling up of quantum processors for practical applications in areas like cryptography, simulation, and optimization. Quantum error correcting codes truly form the backbone of quantum error correction strategies, ensuring that fragile quantum information remains protected and accessible.